methods and also tools from complex analysis to design a new algorithm for a basic problem in learning, which is called the population recovery problem. So let me first introduce that problem, and let me do so by borrowing a story that I've shamelessly stolen from Avi Wigderson. So suppose you're a paleontologist, and you're interested in trying to figure out what sorts of dinosaurs roamed the Earth eons ago. So what do? You dig. And then at each dig site, you might get a hand here, a head there, and a collarbone over there. Now the trouble is that you never, ever, ever get a complete skeleton of a dinosaur. Instead, what you get is a very partial snapshot, just a little bit of fragments here and there. And the question is, can you take these fragments of fossils and stitch them together to a complete and correct description of the entire population? So let me phrase this as a mathematical learning problem, and then I'll tell you later it's natural in its own right, but it's also motivated by some approaches for going beyond sort of the limitations of our current pack learning algorithms. But at least let's focus on this question for now. So can you reconstruct a description of the population from just these highly, highly incomplete fragments? So first, what is the population? So for us, there are k types of species. And each of these species we're going to identify with what sorts of features are present and absent. So each of these species will be a length n string, binary, which is just, does it have this kind of collarbone or doesn't it? So this is our underlying set of strings for the population. And we need one more piece of information, which is additionally we have some probabilities p1 to pk that represent the relative proportions of each of these species in the overall aggregate population. So how could we expect that our samples are drawn? Maybe every time we choose a dig site, well, we choose one of these species proportional to p1 to pk. And then the trouble is that we don't get this full fossil. Instead, we get is an extremely fragmented representation of it. So imagine instead 99% of the string is completely obliterated. You can't tell whether the feature is present or absent. So some of the other ones you can tell, and they show up as either 0 or 1s, but everything else, 99% is gone.
So the dinosaur left a note, I had no collarbone?
Yeah. Now you can see that type of collarbone intact, and it's not of one of the types you're looking for. So essentially, this is actually very different than sort of the standard way you'd think about this from a coding theory perspective, where you'd think of this as some sort of deletion channel. But the difference is that I don't get to choose what these strings are. I don't get to choose them from being a good code for the deletion channel. Instead, I'm just a passive observer to them. So however nature has set up this population, can I still reconstruct a description from these highly incomplete samples? And oftentimes, a sample like this one will be so destroyed that even if we knew these strings, we wouldn't know which one it actually came from. So this is really the source of the problem, is that for each of these things we observe, we don't know the name from which it was generated. So this model was introduced by Dvir, Rao, Wigderson, Yehudayoff. I'll get into in a minute the other motivations for studying these types of things. But just to make sure we're on the same page, this is the Lossy version. So there's an unknown set of k strings, which I'll denote by a1 to ak, and their probabilities p1 to pk. And then the sampling model is that we choose one of these strings proportional to each of the p sub i's, and then we delete. You can think of it as mu is, let's say, 0.01 here. So I'm going to delete 99% of the coordinates. I'm going to flip an independent coin for each of them. So if it comes up with 1 minus mu probability, I'm going to replace it with a question mark. And the sort of basic question here is there a polynomial time algorithm for any fixed mu greater than 0? Is there a question?
The 1% you observe, there's no mistake on it.
That's right, because you know that it's not replaced with a question mark. These things get a lot more tricky when you talk about the noisy version, which you can make the problem even harder in a formal sense, where there's again some unknown set of k strings, probability p1 to pk. And instead, what you're given samples, instead of deleting things and replacing the question marks, what if they're flipped independently with probability half minus eta? So in fact, there you don't know what's been flipped and what hasn't been. And here you could ask the question, is there a polynomial time algorithm for any fixed eta greater than 0? So it's different than the sort of standard coding theory version of this, because these strings aren't from a good code word. So there have been a few papers on this by now, which, the paper at Dvir et al., what it gave, and we'll adopt this framework, is it showed that as long as you preserve 36% of the information, there's a polynomial time algorithm. And there's a technical sense in which half is a very natural barrier, that when you start preserving more than half of the information, this problem becomes very easy, but it was very interesting that they moved beyond this. And I'm just going to give up on the pointer. Subsequently, Wigderson and Yehudayoff, they gave a completely different approach, which they gave a quasi-polynomial time algorithm. And in fact, what they showed was that in that general framework, they actually couldn't get a polynomial time algorithm. So they actually showed a lower bound for a class of techniques. So what I want to emphasize is that actually this question, it's not even clear information theoretically. Should you be able to do it with a polynomial number of samples? There was better analysis by Batman et al., which got 30%, and what I'll be telling you about is going all the way down to 1%. So for any constant mu, even if you just preserve 1%, you can recover the description of the population. And actually the techniques will be some combination of spectral and complex analysis, and I think there's a lot of interesting stuff here left to explore, so I'll say more about that later. But now let me tell you one of the other motivations for studying this, and this will be the last part of the introduction. So here's another motivation, which was actually the original reason they considered it, was think about pack learning. So in the standard pack learning setting, one natural family of hypotheses are things like DNF formulas. A lot of interesting things are DNF formulas. And so what you have is you want to learn some hypothesis for nature, which is a DNF formula, but you have very passive access to this. Because in pack learning, what you hypothesize is that there's some underlying distribution D, that what it does is when you take a sample from D, it sets each of the variables to either true or false, according to some distribution. And what you observe then is you observe the entire configuration of truth assignments, but all you get about the unknown DNF formula is just a single bit, because you know what it evaluates to, either true or false. So it's a very black box type of access to the formula, because all you ever see is just an evaluation of the formula. You don't get to choose its inputs and all sorts of other things. But the trouble with this and with all sorts of other pack learning results is that actually we don't have such great algorithms for this. So the current state of the art is this beautiful paper of Clivens and Servetio, which instead of a 2 to the n type algorithm, which would be trivial, it gets 2 to the n to the 1/3. So it's exponential and n to the 1/3. This is for the distribution independent setting. But even when you look at natural distributions, it actually becomes even worse. Because what if I allow my distribution to be uniform on the hypercube? It's very natural to start with a distribution like that. Then the best known result there is actually just the simple folklore result that who knows who to attribute it to, that you can run in quasi-polynomial time. The intuition is that a log n length clause will never really show up as being on if it's c times log n for a large enough c. So you can just delete all the long enough clauses, and you can brute force search over all the other clauses of not too big size. So in that setting, for uniform distribution learning, for DNF formula, still the state of the art is just the union bound over it. And what we'll see is that, so this is a type of black box access to the formula, and you can wonder, can we move beyond the naive brute force algorithms by getting a little bit better access to the formula? So what if instead you have some notion of gray box access? So instead of just seeing the way that the DNF formula evaluates, what if you see a bit more about its circuitry? So here's a setting in which motivated them to study population recovery. So they called it the restriction access model, where it'll be almost the same as the uniform distribution. The difference is that we're not going to set all of the variables. So what if we set 99% of the variables? So we're setting almost everything, and the variables that get set independently to true or false. But the remaining 1%, these mu fraction of variables, they'll still be live. So what happens there is, if I, for example, happen to set x1 and I set it to be false, this entire clause would get turned off because there's no way it could be true. If instead x8 ends up getting set as true, I would just remove this variable from the clause, and the rest of it would stay live as long as the other variables in it were not set to the wrong values. But the point is that then what you get is for each clause that survives, you get a very fragmented snapshot of which variables actually occur in it. And you have, in a technical sense, the same type of issue, is that each clause that survives, you get some of the variables that arise in it, but you have the same technical difficulty that when I see a bit of a clause surviving, I don't know how to match it up with which clause it originated from. That was the same issue in population recovery, that when I saw a fragment of a species, I didn't know how to match it up to which thing actually generated it. And in a technical sense, an algorithm for population recovery gives you an algorithm for learning DNF formulas where you get potentially better algorithms in this restriction access model than what the limitations of what we can currently do are for the uniform distribution. So in fact, one of the corollaries that comes immediately from what I'm going to tell you about is that actually, even though for uniform pack learning, for the DNF formulas, all we have is quasi-polynomial, once you leave 1% of the variables live, there's actually a polytime algorithm. So that's one of the corollaries, apart from it being a natural problem in its own right. All right, so now I've given you a bit of an introduction about at least what the theorems I'm going to talk about are, but what I'm really excited about this are the techniques, because this talk will really be about just an inverse problem, which I'll write down for you on the next slide, and it's very concrete and explicit, and about connecting better approaches to solving this inverse problem to tools in complex analysis. So what I mean by this is that, as you'll see, there's a way to turn population recovery into a problem of this form, where there's some explicit matrix A, which we'd like to learn something about this vector x, actually just its first coordinate. And instead what we have is we have noisy access to the right-hand side. So we get some approximation coming from taking random samples from our model and computing statistics. Now the natural thing you would think you should do there is you should just multiply by A inverse times your estimate. But the trouble is that B invariably will have some noise in its values because I'm taking a finite number of samples. If I'm taking a polynomial number of samples, I have inverse poly accuracy to the right-hand side. The trouble is that this matrix A has exponentially large condition number, so it blows up the magnitude of those errors horrendously. But the key is that actually we'll only be interested in some of the coordinates of x, and there'll be a way to get around solving inverse problems that moves beyond taking an inverse, that can actually do better even in the presence of exponentially bad condition number. And the way that we're going to do it is we're going to use uncertainty principles from complex analysis. So let me give a little bit of suspense right now. This will be the proof, and I'll show you why that's the proof slowly. So you can think of B as the expectation of the statistics. So if you had B perfectly and you took infinitely many samples, you could just take the inverse and it would be fine. But the issue is that the more samples I take, the finer approximation I get to B, but I only ever get inverse poly accuracy for B. So then it blows it up too much by the condition number. Let's see another view of it. So actually, let me make the problem even simpler, right? So, we have this population recovery problem where we want to know the strings and their probabilities, and we get access to these samples. Let's make it embarrassingly simple first. So what about this easier question? So it seems. Can we find the probability of the all zero string? Let's suppose all zero is one of the strings there. So can we find the probability of the all zero string given these, samples? See, the issue is that when we sample from the all zero string, we get a string with only zeros and question marks, but there are tons of other strings which, happen to have 1, 1. That 1 might get deleted and we get confused. So the issue actually underneath it, which I'll show you in a minute, is actually what we're really looking for is that inclusion-exclusion fails because it doesn't work well with noise. But we're going to give a new version of inclusion-exclusion, which is going to be able to find the probability all zero string. And actually it turns out in a technical sense that this is the heart of the problem. That if you can solve this, you can boost an algorithm for this into solving the entire thing. So I won't get into that, but let me tell you about the setup. So let's try and paint the picture of what our inverse problem is. Our goal is just to find the probability all zero string. And the way that I'm going to set it up is I'm going to set it up as some linear system where each of these values, Q0, is the probability all zero string. This is what I want. So in my inverse problem, there's just a single coordinate I want. So Q0 is the probability all zero string. Q1 will be the total probability of all the Hamming weight 1 strings. So I take all the strings AI, which have just 1, 1, and add up their P sub i's. And the same for all the other Q sub i's. And then this matrix right here, it's going to describe how our observations are related to the statistics we actually want to compute. So, for example, the entry in row J, column I, will just be the probability that if our sample came from a string with exactly I1s, what's the probability that it ends up with exactly J1s? So that'll actually just be a very simple binomial coefficient, right? Because it's just, how many ways can I choose the J1s that survive? This is the chance of them surviving. This is the chance of the other guys getting deleted. So this is a very explicit matrix, but the trouble is that it's a horribly conditioned matrix. Because in fact, it's upper triangular, and all the entries along the diagonal, they get exponentially small. So this is the sense in which taking the inverse of this is a futile task, and you don't even necessarily know, is this problem solvable with a polynomial number of samples, right? So just to complete this picture, right? So, if this is my linear system, what would B0 be? Well, the interpretation of it is, all it is just the probability that when we take a sample from our model, that what we observe has only zeros and question marks, right? So that we get a string that looks like this. The same way B1 is the probability that we observe just one, and the rest of them are zeros and question marks. So we observe something like this. Now the trouble is that we only get a noisy approximation on the right-hand side. This matrix is invertible, so if you told me these statistics perfectly, I could take A inverse and I'd be done. But the more samples I take, the finer and finer approximation I get to these things, just taking their empirical averages. The question is inverse poly accuracy enough to actually recover Q0 in this problem? So, I talked about this already, but let's say B bar is our empirical approximation to B. We take A inverse times B bar, we take its first coordinate. Terrible strategy because of the condition number. So another way of thinking about this, actually, which will be very fruitful, is let's take a vector E0, right? Which is a vector in which there's 1 in the first coordinate and everything else is 0. And now if I multiply this by A inverse on the right, I get some vector x. And this x here is an estimator, because when I take my average B and I take their inner product, well, we can write out explicitly what it is. I write out what x is, I get an A inverse. I write out what B is, I get an A, and they cancel. So what this x is it's a linear way to combine the statistics I have access to in a way that it's an unbiased estimator for the thing I want to compute. Now the interesting thing is that, I claim that this naive strategy fails. The way that this manifests itself is that x, if you work out what this is, has exponentially large norm. So it's an estimator which is unbiased, but its variance is off the charts. And that's not an accident. This is the only estimator that's unbiased. So the issue is that there is no unbiased estimator with small, sub-exponential variance. So can we construct a new estimator which actually does have some bias, but completely gets rid of all of the variance? That's the technical question. There's another view where this x is really, it's an inclusion-exclusion formula if you work out what it is. And we're looking for a new inclusion-exclusion formula.
So if you try to throw away some of the eigenvalues of A, would that help? Or?
No, that's a very good question. So let me take a second to say the intuition about this. So let's say mu is a half. So I'm equally likely to delete a coordinate as to keep it. So then what's a naive way to estimate the probability all zero string? I can look at first what fraction of strings have no ones. That'll be an upper bound on my Q0. Then when I see 1 and the rest are zeros and question marks, I should think, crap, I'm equally likely to have deleted that 1 as kept it, so I should subtract 1 from my estimate. And I can keep correcting it in this way, and I get +1, -1. But as soon as you're more likely to delete something than keep it, your corrections grow exponentially. So actually truncating this thing would also be a bad idea, which is what actually getting rid of the small eigenvalues does. So that's part of the issue, is that you need to get the same cancellations with the right way to damp it as it's growing exponentially. So what that is here's one way to try and fix this. So the issue is that when I take E0 times A inverse, I get exponentially large norm. Is there some magical perturbation eta which somehow moves E0 entirely off of all of the small singular values? So is there, this eta here will be the bias of my new estimator. So can I add some eta so that this new x bar doesn't have large norm? It has polynomial norm, so the variance as an estimator is not too bad. And when I plug it in, what it's computing, it's off from Q0 by some term that depends on eta. So the question is there some magical bias that I can add that allows me to completely remove the variance of my natural estimator?
I mean, I'm not sure if I'm understanding correctly your error, your model for the error.
Yep.
But the usual thing that one would think in this case is to do regularization. right? Reconstruction or something like this. I mean, why that doesn't work in here, or
Let me table that to the next slide. Good question. So this is the strategy. It's called a robust local inverse. So the fact that we only want to compute one value of q, q0, is going to allow us to do better than the inverse. Now, actually, 2 slides, sorry. So actually, the main theorem here is just when there is a good robust local inverse. So Dvir et al.'s approach when they got 36% for population recovery was just that this matrix has a robust local inverse for any mu greater than 0.36. And that's what all of these things were doing. In fact, they conjectured that it didn't work, the approach didn't work beyond 1/4. But I'm going to show you that actually there is a robust local inverse for any mu. And one of the tricky things to deal with is like, what does this robust local inverse look like? What should this perturbation be for how do I bias my estimator in the right way to remove its variance? And to get to Pablo's question now, actually, whatever this robust local inverse is, there's always a way to write it as a convex program. The issue, though, is how good does that convex program behave? So it'll find the best robust local inverse. Why does it find anything good? So that's what the analysis technique will be. So what I'm claiming is that this idea of actually trying to perturb x off of, perturb E0 off of itself, we can write in another way, right? So x initially we had as E0 times A inverse. But now what I want is that I want that it's not that far off from E0. So for example, I want that my new estimator is not biased by much off of what it should be. This is the accuracy constraint. Now what about the insensitivity? I want the norm of x to not be too large. That way, when I'm getting random samples from my model, this guy doesn't have too much variance, that I can't just take enough samples and get some confidence about what its expectation is. So the same way plugging in x equals E0 times A inverse would not work. It would satisfy the first thing with epsilon equals 0, but the bottom thing would be exponentially large. That's another way of saying that no unbiased estimator can possibly work. Now this is just a convex program that I can solve, but the question is, why should there be a good solution at all? We want to say that for any mu there actually is a good solution in this convex program. And instead what we're going to do, instead of reasoning about the primal and guessing a good x, for example, you're going to pass to the dual. So we're going to instead prove that the dual has no good solution, and hence this convex program has to find me a good estimator. That's going to solve this population recovery problem. And the way that we're going to do it is we're actually going to choose a natural basis of estimators. So this is the part where I'm going to, you're going to believe me, hopefully. And then I'm going to pass to where we get into complex analysis. It turns out that, what you can do is instead of asking, is there an x? What if I consider some estimator of this form? So powers of alpha. None of these estimators will be good. But I can choose a bunch of different values for alpha and ask, is there a way to create a linear combination of these estimators that is good? It just so happens that this is really a change of basis that turns this question more into a problem about monomials of polynomials. The same way, sorry, what?
Sorry, what is alpha?
Right, what I'm saying is instead of guessing a solution x to this, let me instead choose a bunch of different values of alpha and look at these moment curves and ask, is there a good linear combination of these estimators that's a solution to this convex program? So this actually happens to be a nice basis where the constraints work out nicely because, we have binomials here. So when we have estimators of this form, we can just do binomial expansion.
So you're saying x would be the sum of vectors like that for different values of alpha?
Exactly. But my point is just that this actually transforms the problem into a much nicer form. So this is the part you're going to have to believe me, but let me tell you the new form of this convex program. So it turns out that it turns this convex program into what look like constraints on monomials of polynomials. So the dual program actually asks to construct a certain type of polynomial. And if we can prove that there is no polynomial of that form, it'll actually imply the dual program has no good solution, the primal has to have a good solution, and we can find it, which will solve our problem. So that's the basic outline. Let me tell you what that polynomial question is. That's where complex analysis is going to save the day. So the dual program wants to do the following. So this is the sort of technical part that I'm going to focus on. All the rest was sort of claiming that this problem, which will just be a statement about polynomials, is going to give us new algorithms for population recovery. But this is what the technical problem is. So is there any polynomial p, which let's say it evaluates to 1 at the origin. So it's normalized. You can't make its coefficients too small and rescale it. But you want to know if this polynomial can be 1 at the origin and yet hide its coefficients in 2 different bases. So this coefficient norm I'm using just for the sum of the magnitudes of the coefficients. And q here is related to p by some affine change of basis. This is where the mu parameter comes up, is because as mu gets smaller and smaller, population recovery problem gets harder and harder, but q and p become closer and closer to the same representation. Now these are 2 slightly different representations, and what we want to know is if you're 1 at the origin, does it imply that your coefficient norm is large in at least one of these 2 representations? So this is a type of uncertainty principle. The usual version of uncertainty principle is you take 2 very different bases, like the standard basis and the Fourier basis, and you show that, if you're normalized, then you have to be large in one of the 2. But here, these 2 bases are getting closer and closer together, and we still want to prove an uncertainty principle. So that's what we want to show. We want to show that, this uncertainty principle, and this is relaxation 1, so this is not going to work. But the coefficients of a polynomial are actually very difficult to reason about. So one thing you can try is you can try a relaxation of it. Because what I claim is that the coefficient norm of a polynomial, so the sum of the absolute values of the coefficients, is lower bounded by the max value of the polynomial on the interval -1 to 1. This is just triangle inequality. Because the absolute value of p of x at some value x in the range -1 to 1 is just lower bounded by the coefficient norm, just triangle inequality. So this gives us a different question. Is we want to know if a polynomial is 1 at the origin, can its max value in 2 different representations be small? So with this actually, here all I've done is replaced what q is by p. So what we're really asking is the value of a polynomial a lower bound for some epsilon times its value on max value in -1, 1, plus some huge constant c that depends on epsilon, times its max value in some restricted range. And actually, the trouble is that there are polynomials that do this. So let's think about what these polynomials could be. See a counterexample here. It would be 1 at the origin, and it would never get too large. That's the sense in which its representation is reasonable in one basis. So let's say this polynomial should be at most 1 over epsilon on the entire interval -1 to 1. And then also, this part right here, we need this part to be extremely small. So this is just evaluating the polynomial at 1 minus 2 mu to 1. So we're forcing the polynomial to be extremely small here. So the question is, if I force a polynomial to be really tiny here, 1 at the origin, and not too large on the rest of the region, does that rule out everything? Is that a growth pattern that's allowed for polynomials? And there is one. What I can do is I can put n over 2 roots at +1 and n over 2 roots at -1. This guy is exponentially small here, hits 1, and then goes all the way back down. So it sort of kills us because actually, so the thing to think about is, does this polynomial refute our conjecture? And the question is that, this is a polynomial which is 1 at the origin. Are its coefficients small in different bases? And what I claim is that no. Because one thing we can do is we can plug in x equals I here. What that does is it means that p of x evaluates to something exponentially large. So we have a polynomial which is 1 at the origin, but it hides on the real line, but it escapes in the complex plane. So that's the key, is that's why complex analysis will provide a solution to this, is it gives us a new relaxation. Instead of using this lower bound, that the coefficient norm of a polynomial is lower bounded by its max value in -1, 1, that's bad, because drawing a polynomial in the real line doesn't tell you much about its coefficients, but drawing it in the complex plane does. So this gives us a new question. Well, we ask instead, let me just phrase it this way. We have our polynomial, which is 1 at the origin, but now it has to be 1 over epsilon on the entire complex disk. And this new disk right here, centered at 1 minus mu, it has to be really tiny there. So the question I asked earlier was just a slice through this. And actually what I claim is that, see we want it to be 1 at the origin, at most 1 over epsilon on all of the standard complex disk, and really, really tiny on the smaller disk. And we asked before was just a slice through it, right? Because there were polynomials that could hide here, but they end up escaping up here. And actually, there is no such polynomial. So that's the last part I'm going to show you, is that once you're in the complex plane, you have these beautiful results about growth rates of nice functions. So one of them is this Hadamard three-circle theorem, which tells you that if you have three concentric circles, and you take the max value on this disk, the max value on this disk, the max value on this disk, that the max value here is bounded geometrically by a product of these two maxes. So what it tells you is that if you're really tiny here, and you're 1 someplace here, you have to grow really fast at some point. So it's really just saying that things behave like nice polynomials that you'd expect them to. This is the quantitative version. But now what this tells us is that, how do we want to prove this? We want to say that if you're really tiny here, and you hit 1 here, it's impossible for you to stay bounded everywhere in the complex disk. And the way that we do that is the picture I drew earlier. We just draw another circle in between. It's not quite 3 concentric circles. So what you do is you take this growth pattern that can't exist, and you take a Mobius function that actually maps one diagram inside the other one. So this is the Hadamard three-circle theorem. And the Mobius transform is going to map this outer disk to the outer disk, this smaller disk inside, and then this disk will hit the origin at some point. So it allows us to sort of rule out certain types of growth patterns that, what the overall outline now is, just to conclude actually, is that we used uncertainty principles from complex analysis to rule out certain growth patterns for polynomials. What that did was we had this convex program for finding the best robust local inverse. That program is feasible. It has a good solution, which, because we proved the dual, isn't feasible. So that allowed us to construct a robust local inverse that gave a polytime algorithm for population recovery. So, sorry, how much?
Extremal function?
What?
What are the extremal functions for the Hadamard?
So they're fairly simple, so I can write them down later. But they have to be composed with Mobius transforms anyways to be extremal things for this. For the question that I actually care about. Yeah, exactly. But so I wanted to show you a little bit about how some of these, strange functions that arise in complex analysis can actually give you new algorithms in learning. So this is sort of the main statement of the results, is that there is a robust local inverse for any mu greater than 0. And we got a polynomial time algorithm for lossy population recovery and for learning DNFs in the restriction access model. So I'll quickly summarize and tell you the open questions. So this, I thought, was an interesting example where you're solving an inverse problem, but it's horribly conditioned. But by virtue of being interested in just some coordinates of it, you can actually do much, much better than actually taking the inverse. So these robust local inverses can give you completely qualitatively different behavior in some settings. We use tools from complex analysis. So natural question is, can we use robust local inverses for other problems in statistical inference and other sorts of inverse problems? And is there a polytime algorithm for the noisy version of it? So I'll stop there, but thanks. All right.
So, for the noisy version, you can write it in the same way, right? You can write a matrix, it would just be a different matrix.
Yep.
And it just becomes much harder to analyze.
The uncertainty principle fails there.
So it's not true.
Yeah.